Okay, so last time we derived two of the more important equations for the class. So we looked at the derivation of the wave equation. And then after that, we looked at the derivation of something called the diffusion equation. And so remember, the wave equation turned out to be a second order equation in time. And so it says that if you take the second partial derivative with respect to t of your function, then that has to equal some number c squared times the second derivative with respect to x of u. Or another way of writing this is utt is equal to some c squared times uxx. And so this was the one-dimensional version of this equation, right, which we derived. And then we moved on and looked at the diffusion equation, for which we considered the three-dimensional case. And so this instead was a first-order equation with respect to the time derivative. And so it says that if you take derivative with respect to t of u, then this is some constant, say k, some different constant, which is related to the physical properties times the Laplacian of u, right? And so again, another way of writing this is maybe ut is equal to k times Laplacian of u. And we did this in 3 dimensions, right? And so we also considered, or at least I just told you, that there are analogs of the wave equation, for example, in higher dimensions. So if you look at the wave equation, for example, in dimension 3, instead of just dx applied twice here, you would replace that by the Laplacian, right? So in 3 dimensions, the wave equation has the form utt is equal to c squared times the Laplacian of u, right? And so for the bulk of the lecture today, we're going to be focusing on how to solve the wave equation in just 1 dimension. Before we do that, though, I just do want to mention a few more things related to variance of the diffusion equation, which are worth pointing out now. Right, and so the first is that there are, I mean, the argument we gave was specific to 3 dimensions, but there's also analogs in 2 and 3, in 1 and 2 dimensions. Right, and so in 1 dimension, what does the equation look like? Well, it's going to look very similar to the wave equation, except you just have a first order derivative. So it's derivative with respect to t of u is equal to some constant k times the second derivative of u with respect to x. And in 2 dimensions, you're going to have, well, the first derivative, or the derivative of u with respect to t is some number k. Now, instead of just uxx, you have uxx plus uyy. And so that's the same thing again as k times the Laplacian of u, but now the Laplacian is the 2-dimensional Laplacian, right? And so, right, so these equations, they have more compact forms, which are kind of independent of the dimension, as long as you understand which dimension the Laplacian is referring to. So you can write these instead as maybe utt is c squared Laplacian of u, or ut is equal to k times Laplacian of u. And so these are kind of the more general forms of the wave or diffusion equations, which you'll typically see. And so the dimension of the Laplacian will be given to you from context. Oh, sorry. Great. Right, okay, and so the argument in one and 2 dimensions are going to be very similar to the argument we gave in 3 dimensions. So you're going to use some version of Fick's law, which says that the change in the amount of whatever the substance that is diffusing in a small ball is going to be, the rate of change is going to be proportional to the rate that it leaves the boundary of the ball, right? Okay, and so there's another very important equation in physics which is related to the diffusion equation, which is known as the heat equation. And so this describes, right, so imagine you have, let's do heat equation, right? So imagine you have like a heated plate. Right, so maybe there's like a few different source points where you have some heat sources. Maybe there's a heat source here, and maybe a heat source here, and a heat source here, and you let time evolve, and you consider how the heat spreads out across the plate. So let's say my function u, right, let's say this is in, let's say for simplicity we're in 2 dimensions. And so let's define a function u of x comma y, which is the point at time t. And so let this be the temperature of the plate. And so when I say plate, I mean like maybe like a metal plate, like a block of metal. And so let's let this equal the temperature of the plate at point t, or point xy and time t. Right, so maybe initially, like if you look at where I'm drawing the blue dot, maybe at this point when time is very close to 0, the temperature is going to be very large because it's near the heat source. But maybe if I look at another point over here, the second blue dot, initially the function u is going to have small value because it's not that hot yet. But over time, the heat's going to spread across the plate, and so the function u will change with time. So that's what this function is. And so it turns out that this phenomenon of heat flow, at least if the object you're heating up is relatively uniform, this phenomenon is very similar to diffusion, right? So you can imagine like the heat as like tiny particles that are moving or spreading out across the surface, and so that's basically a diffusion type phenomenon. And so this is reflected by the fact that the equation that describes heat flow looks a lot like the diffusion equation. So what is the heat equation? It takes the form, well, you have some constant c, and then some other constant rho times the time derivative or derivative of u with respect to t. And this is equal to, well, you have some other constant, which is usually referred to as the Greek letter kappa times the gradient of u. And then you take you apply the divergence operator, right? Which means you just take right, so this kappa times gradient of u is a vector. Remember this divergence operator, you take derivative with respect to x of the first component, and then add on derivative with respect to y of the second component, if you're in 2 dimensions. If you're in 3 dimensions, there's one more term corresponding to the third variable, or the third component. Right, and so depending on, so this constant, or this number kappa, depends on properties of the actual material you're looking at. And so it could be a constant, or in more complicated situations, it may not be a constant. So I'll just put may or may not be constant in x and y. Right, so if you have like a more complicated surface where maybe parts of the surface are made up of one type of material and then parts of it are made up of a different type of material, then the kappa wouldn't be constant. Right, and so this constant c is related to the specific heat. Rho is going to be a stand-in for the density of the material. And so kappa reflects the heat conductivity of the material. Right, and so these are all various physical parameters which don't matter too much for us because this isn't a physics class, it's a math class, but I at least want to indicate where these different numbers will come from. And so notice that in the special case, well, let's see what happens if kappa is constant. It's going to turn out that this equation will just reduce to the diffusion equation, right? So if this is constant, So the right-hand side becomes, well, since it's constant, I can factor it out of the divergence operator. So I just have kappa times the divergence operator applied to gradient of u. But it's an easy calculation to see that the divergence of the gradient is the Laplacian operator. So you get kappa times Laplacian of u. And so in this case, well, the heat equation becomes time derivative of u is equal to kappa divided by c times rho, and then times Laplacian of u. So this is just the diffusion equation again, with maybe a different constant. Right, and so again, this is related to the fact that at least kind of heuristically, you expect heat flow to be very similar to like this diffusion phenomenon. And there are more kind of sophisticated explanations for why this is the case, which maybe we'll talk about later in the semester. Right, and so I just wrote down this equation of the heat for heat flow and just told you why it's potentially similar to the diffusion equation. I didn't explain where this equation actually comes from. So the derivation is in the textbook if you're interested in looking at that. The argument is very similar to the derivation of the diffusion equation, so I'm not going to repeat it here, although I would recommend reading the section in the book. So let me just put this as a note. And this is expected, right? Because the equation has a very similar form to the diffusion equation, so the derivation should probably be very similar. The big difference is that instead of using Fick's law, which is about like the diffusion of some substance, you're going to use the law of conservation of energy. And so what the law of conservation of energy basically tells you in this context is that if you look at, like say you fix a tiny ball on the plate, well, it basically tells you that the only way that the total amount of heat can change in that ball is if it's leaving through the boundary, right? Otherwise, the energy or the amount has to be conserved. And so this has mathematically, this basically gives you the same formula that we got when we applied Fick's law. And then after that, the analysis is the same, and you get a very similar equation. And it's worth here, I guess, also adding that, remember, there is, I mean, for a different physical situation, you're going to have to use different methods to derive a partial differential equation that explain what's going on. But there are a few general principles that are always used, and the basic, like how did all of these arguments work? Well, as a first step, we tried to understand physically what was going on, and there was some very important law from physics that describes the system, right? So when we look at the wave equation, we ended up using Newton's second law of motion. And when we looked at the diffusion equation, we used this Fick's law. And so then these laws from physics will typically, as long as you apply them correctly, they'll typically give you some rough version of the equation. And then once you get to that point, you have to do some mathematical analysis to put the equation into a more tractable or into a simpler form. And so all these derivations work in some way and like this. Okay, and so finally, I also want to mention one more variant of the heat and diffusion equations, which actually turns out to be related to the wave equation as well. And so this is something called Laplace's equation. And so this is best thought of in terms of the example we just saw before, right? So consider a heated plate. Right, so maybe there are some different heat sources on this metal plate, and then you let time evolve and the heat is spreading out. And so suppose we let time t go to infinity, right? So I have some function u of x, y, t, which is describing the way the heat spreads out. And so eventually, right, in the limit as t goes to infinity, we expect some kind of equilibrium to be reached. Right, so we expect that at a certain point, there's going to be some uniform distribution of the heat, and it's not going to be spreading out much more, right? So distribution, by equilibrium, I mean that eventually the distribution of the heat won't change with time. Right, I mean, for example, if instead of the 2D case, you consider the 3D case, like when you turn on an oven, right, imagine that you're considering the way the heat flows in the oven. Well, there are certain heat sources on the sides, and after a certain point in time, basically all of the oven has the same temperature distribution, and it's not changing anymore. So that's sort of what we're looking at here. Well, if you're in this equilibrium state, what does that mean mathematically? It means that there's no more change with respect to t. So that means that if I take the time derivative, it should be equal to 0, right? But if this function describes the heat flow, remember we have this other formula, the heat equation, which was time derivative is some constant times the Laplacian. And so, well, if ut is equal to 0, this gives me a new equation where instead of time derivative with respect to t, I just have 0 on the left-hand side. And since I have a constant here, I can just divide by that constant, and I get Laplacian of u is equal to 0. And so this is what's known as Laplace's equation. And this is the reason why this operator, this triangle is called the Laplacian, because when you look at Laplace u equals 0, this gives you what's called Laplacian's equation, or Laplace's equation. And so this is sometimes also called the steady heat, or I guess steady heat equation. I may be saying that wrong. But it's like a steady state heat equation, right? Sorry. So there's no more evolution with respect to time. And so, right, so it turns out that the theory of this equation has a lot of implications, not just in physics, but also in pure math. So it's a very important partial differential equation. And so we're going to analyze this equation in I guess in about a month from now. So what the plan for the rest of the class, at least for the next month or so, we're going to spend about 2 more lectures talking about the basic theory of the wave equation in detail, and then a few more lectures after that talking about how to solve the diffusion equation. And then we're going to look at slightly more complicated variants of these problems, and then after that we'll move on and look at Laplace's equation. Right, and so the main 3 equations for the next month or so are going to be first the wave equation, which we're going to turn to in a minute, and then we're going to look at how to solve the diffusion equation, and then after all of that, we'll talk about how to solve Laplace's equation as well. Okay. All right, so the next thing to turn to then is now how to solve the wave equation. So we're now moving on to chapter 2. Right, and so remember the wave equation has the form second derivative with respect to t is equal to some constant c squared times second derivative with respect to u. And so I can rewrite this as utt minus c squared uxx is equal to 0. And so what we're going to do is find solutions on, again, we're looking at this in one dimension, and we're going to look at the domain where x is just on the whole real line, right? So my function u is a function of x and t. We're going to find solutions when x is just in the unbounded domain of which is the whole real line. And then in a few weeks, we'll talk about how to solve this in more restricted domains, like say a bounded interval or something like that. So it turns out that for this equation, at least, it's easier to find the solutions first if you look at the case when x is just allowed to be on the whole real line. Right. Okay, and so the first observation you can make, which helps actually arrive at the solution, is to use this perspective of viewing this as a differential operator applied to the function. And so I can write the equation in the form, well, I have, right, this second derivative with respect to t operator minus c squared times second derivative with respect to x operator applied to my function u. And so if you look at this formulation in terms of these different derivative operations, this should remind you of a formula from algebra. Let's say you have, like say, some number a squared minus some number b squared. Well, remember you can factor this as a minus b times a plus b. So this, at least algebraically, the expression involving the operator on the left has basically this form, right? So I'm saying a is like taking derivative with respect to t, and so I'm squaring it because I'm applying it twice in a row in the first term. And so b is basically whatever the constant c is times derivative with respect to x, right? And so I'm applying that twice because I'm taking 2x derivatives and then multiplying by c twice, or getting c squared. And so this leads you to conjecture that, well, you can probably factor this as d dt minus c times d dx applied to d dt plus c times d dx. And then I'll apply to u. Right, and so what does this actually mean more specifically? It means, well, first take these derivatives and then apply the second operation. Right, so maybe just to clarify what I mean, right, so this is equal to the operator on the outside. And then what do I have on the inside? I have ut plus c times ux, right? So I applied the first operator that's closest to u. And then now I have this new function, but the right, ut plus cux is a new function, and now I'm going to apply the second operator. And so what do I get? Well, I'm taking the derivative with respect to t. So if I apply that to the first term, I get utt. Now let me apply the d dt to the second term, so I get plus c times uxt. And now let me apply the second piece. So right, so I'm distributing this like I would distribute multiplication, and you can do this with differential operators as we saw before. And so now applying minus c d dx to ut gives me minus c utx. And then applying it finally to the last term gives me minus c squared d dx of ux, which is minus c squared uxx. But the two middle terms are equal, or at least they're equal but of opposite. So they're equal in absolute value, but they have opposite sign, right? So they're going to cancel out. And this is just because uxt is equal to utx, right? Because remember, you can always swap partial derivatives. And so these terms just cancel out and give me 0. And so I get exactly what I expected, right? Right, and so what this little calculation shows is that this guess related to this formula from algebra is actually valid. So I can actually factor my operator in this way, right? And so what we just proved here is that which is really just a calculation in taking derivatives. It's kind of a simple exercise. So we just proved that the wave equation also has the form well, you first apply this differential operator d dt plus c times d dx to u, and then you apply the second operator d dt minus c times d dx, right? And that all has to equal 0. And so the reason why this is helpful is because, well, if you look at, well, let's look at what I have in brackets here. This is, if you just consider this operator, this should remind you of like a first order linear equation. Right, and in fact, what I really have here are two different differential operators, both of which, if I just set them equal to 0, would give me first order linear equations, and we know how to solve these, right? And so we're gonna use this as a guide to actually arrive at the solution, right? And so how are we gonna do this? Well, let me define, say, v of xt. I'm gonna define a new function, and this function is going to be what's in the brackets. So I have d dt plus c times d dx of u, right? So v is just the first derivative with respect to t of u plus c times derivative of u with respect to x. And so the equation above is just well, if I plug in v here, I get vt minus c times vx is equal to 0. And this is indeed like a first order linear. And so we know how to solve this without, I mean, if we don't have initial conditions, we don't know what the exact solution is, of course, but we know what the solutions look like. So we know that this function v of xt has to equal some function, let's say h of x plus ct, right? Right. And so this was from the theory before, for some function h, right? And so then what happens to the wave equation above? Well, now I know what v is. And so what is the wave equation becomes, well, v is equal to ut plus c times ux, right? So remember this was v, and we just saw that v has to equal some function h of x plus ct. Right, and so now this is once again a first order linear equation, but it's now a non-homogeneous version of the equation. Right, so we don't actually know how to solve this particular equation, but we know how would know how to solve it if h happened to be equal to 0. And so it turns out that, well, in this case, we're just going to get lucky, because if you just inspect this, you can just kind of guess the solution. And so you can guess and check, well, if I let u of xt equal, say, some function f of x plus ct, what condition do I need on f in order to solve this equation? Well, let's just look. So if I take derivative of u with respect to t, that has to equal c times f prime evaluated at this point. And if I take derivative of u with respect to x, this has to equal just f prime at the same point, right? Right, so if I take ut plus cux, that's going to give me that's going to give me 2 times c f prime. And so I want this to be equal to h, right? And so if f is just an antiderivative of h, I have a solution, right? So choose any f, right? So choose my function f, let's say f of z, such that if I take derivative of f, then I recover h. Then I almost have a solution, but remember I have this extra factor 2c here, so I just want to divide by 2c, right? So let's say f prime divided by 2c is equal to h, right? And so any such f will give me a solution, right? And so then what we just showed is that u of xt equals f of x plus ct is a solution. Right. And so it's going to turn out that this is a good motivation for finding the complete solution, but this is not the complete picture. So it turns out that the actual solutions to this PDE can be a little bit more general than this. We can see why just using this perspective here, because, well, right, let's go back and look at the equation that I'm boxing off now in red. So we found one general form of a solution, but notice that I'll just put this as a remark. Suppose I have any solution to the homogeneous version of this linear equation. So suppose, let me call it u tilde is a function with, let's say u tilde t plus c times u tilde x is equal to 0, right? So now I'm replacing h by 0, right? So this is the homogeneous equation. Well, if I add this function to u, I'm going to get another solution to my original problem, right? So the claim is that if I add, right, so u plus u tilde, I take the t derivative, and then plus c times u plus u tilde. And the claim is that this also has to equal h of x plus ct. And this is just because the equation on the left-hand side is linear, right? Because, right, so what do I have here? I have ut plus u tilde t. And then I have, for the second term, I have c times ux plus c times u tilde x. And so I can rearrange this now as ut plus c times ux, and then plus just collecting the like terms, plus u tilde t plus c u tilde x. And so the first term we saw, based on our choice above, is just h of x plus ct. And the second term is 0, right? Because this solves the homogeneous equation. And so this is another solution, right? And so it turns out that the general solution is going to be found by basically adding a solution to the homogeneous equation to the solution that we just found, right? And so, well, we know how to solve the homogeneous equation, just because, again, we spent the second lecture discussing this methods. And so from the second lecture, well, we know that, right, so this u tilde is a solution to the PDE derivative with respect to t plus c times derivative with respect to x is equal to 0. Well, we know that the general solution for that was some function g of x minus ct for some g, right? And so what this tells us is that we expect then the general solution to be of the following form. So we expect it should be u of xt is equal to, well, we had the function f of x plus ct, and then we added on this other solution plus g of x minus ct. Right. Right. And so this, I don't know if you remember from your ordinary differential equations class, this should remind you of this method for solving non-homogeneous ordinary differential equations, where you first look for a particular solution to the non-homogeneous equation, and then you add on a solution to the homogeneous equation. And as long as it's linear, this will always give you a more general solution. And so that's kind of what we're doing here, but we're doing it for the partial differential equation rather than the ordinary differential equation. Right. Okay, and so this is, I mean, this is kind of like a very maybe sort of unmotivated derivation of what the solution should look like. Like I'm using a lot of algebraic tricks and then a lot of tricks related to the linearity. So that's maybe one problem with this specific argument. And so there's also a more serious problem, which is, well, I showed that if I add two functions of this form, that gives me a solution, but this doesn't actually show that all the solutions have to look like this. And so what we have to do is actually prove that these are the only solutions we can get. And so the way we're going to do this is by re-deriving the formula I have here boxed off using a different method, which turns out to be related to this coordinate method, which was discussed in the book in section 1.2. And so if you found like this derivation to be not very intuitive, maybe this, I'm gonna give a second derivation, which actually will prove that this formula I have boxed off is the most general solution formula. And so I'll write this as a theorem, right? So suppose u of xt solves the wave equation. And again, we're looking at the domain where minus infinity is less than x, which is less than infinity. So the theorem is that there are two functions of one variable f and g such that the above formula actually holds. Right, so such that u of xt is equal to f of x plus ct plus g of x minus ct. Right, and so we're going to prove this now using a slightly more rigorous argument than what we did above here. Okay, and so here we're going to use a version of the method of coordinate changes. Or I guess the book calls it the coordinate method, something like that. The motivation is, well, let's look at the formula we saw before. Right, so let's say I call the input of this function this letter xi, which is pronounced like, so it's like the Greek, it's a Greek letter xi. And let me call the other input eta, right? So this is the Greek letter eta. And so what I'm going to do is I'm going to let xi equal the input of the function f, which is x plus ct. And then I'm going to let eta denote the input of the function g, which is x minus ct. And so the solution, our candidate for the solution, which we arrived at using kind of the intuitive algebra calculations above, well, it says that u is just some function of whatever this xi is plus some function of whatever this eta is. And so the idea is, well, maybe let me change my coordinates for the xy plane and introduce new coordinates where the first coordinate will be xi and the second coordinate will be eta. And then in terms of these coordinates, the formula seems to be much simpler. So maybe it's easier to prove if I use these coordinates. And so that's what we're going to do. Right. So we're going to change coordinates to xi and eta instead of x and t. And so you should think back to like these change of variable formulas for integrals that involve the Jacobian when you do a change of variables in the plane. We're just doing exactly that type of change of variables, but there's no integrals, so the Jacobian isn't going to be relevant. But we're just changing our variables or changing our coordinates from xt to these slightly more complicated coordinates, which will, even though they look more complicated, they'll actually simplify the equation. And so we have to do a little bit of algebra and calculus to make this change of coordinates work. So this is the next step. So the first thing to point out is, right, so to look at is how do the two differential partial derivative operators change, or how do they change when we look at these new coordinates, or what do say d dx and d dt look like in the new coordinates? Well, we can understand this by using the chain rule. So in particular, if I look at the derivative with respect to x of u, I want to use the chain rule to relate this in some way to xi and eta. Notice that x is a function of xi and also a function of eta just by looking at the formulas above. And so the chain rule tells me that this should be equal to du dxi times dxi dx plus du d eta, times d eta dx, right? Because because there's some dependence between xi and x and between eta and x. And so similarly, if I use the chain rule with respect to taking the partial derivative with respect to t, well, derivative of u with respect to t should equal derivative of u with respect to xi times derivative of xi with respect to t, and then plus derivative of u with respect to eta times derivative of eta with respect to t. And so now if I have to actually do some calculations now to figure out what all these terms are that I've just highlighted. And then once I figure out what these terms are, I have relations between the x and t partial differentiation operators, and then the differentiation operators in the new coordinates. Great. And so let's first actually, if what I just said didn't make any sense, let me just first calculate these four terms and then plug in, and then it'll become a little bit clearer what I'm doing, hopefully. Right, and so we can calculate, well, I know c is equal to x plus c times t. So derivative of c with respect to x is equal to derivative with respect to x of x plus ct. So that's just 1. Now derivative of c with respect to t, derivative of eta with respect to x is equal to derivative with respect to x of, now eta is x minus ct, and so that's also equal to 1. So we have the first two terms. And now we just need to look at the t derivatives. So derivative with respect to t of xi is derivative with respect to t of x plus c times t, which is c. And then derivative of eta with respect to t is d dt of x minus ct, which is minus c. Right? And so I can now plug these in to what I got using the chain rule. And so this tells me then that derivative with respect to x of u is the same thing as derivative with respect to xi of u plus c times derivative with respect to eta of u, and also derivative with respect to t of u is equal to derivative with respect to xi of u minus c times derivative with respect to eta of u. Right? And so this works for any u. Right? And so since these formulas hold for any function u, this tells me that well, taking derivative with respect to x is the same thing as taking derivative with respect to xi, and then adding on c times derivative with respect to eta, and also derivative with respect to t is equal to derivative with respect to c, and then minus c times derivative with respect to eta. Oh, excuse me. I just realized I made an algebra mistake here. So when I looked at derivative with respect to x, remember d eta dx was just 1. So this should have been a 1. And then there should be a c in front of here. Right, because d c dt was equal to c, and d eta dt was equal to minus c. So sorry about that. Right, so the correct formula is that derivative with respect to x is derivative with respect to c plus derivative with respect to eta, and then derivative with respect to t is equal to c times derivative with respect to c minus c times derivative with respect to eta. And so these are our formulas. And so what all these calculations say is that, right, so if I introduce these new coordinates as before, we just derived how the differentiation operators transform in these new coordinates, right? So what do partial derivatives with respect to c and eta look like in terms of partial derivatives with respect to x and t? So that's what these equations say. And so what we're going to do now is return to the formula for the wave equation and see what do we get. Well, recall, what does the wave equation say? Well, we factored it before. We had d dt minus c times d dx times d dt plus c times d dx applied to u is equal to 0. And so what we're going to do now is rewrite this in terms of the new coordinates c and eta. So we have, for example, let's look at the first term. So what is d dt minus c times d dx in terms of the other coordinates? Well, this is the first time I'm going to plug in c times d dc minus c times d eta. And the second term, I have minus c times d dc plus d eta. And so this is going to simplify. Well, I have two terms which will cancel, which is c times d dc and negative c times d dc. And then I also have two terms which will combine. So I end up with, if you do the algebra here, you have minus 2c d eta, right? And so this first term only depends on eta. So this is equal to minus 2c d eta. And then, well, now let's look at the second term. So this is d dt plus c times d dx. And so once again, I'm going to plug in the formulas we derived above. So we have, for d dt, we have c times d dc minus c times d eta. And then we have plus c times, plugging in for the x partial derivative, d dc plus d eta. And so now the terms involving eta will cancel out, and I'm left with 2 times c d dc. And so the second term in this factorization we had only depends on the other variable, on c. And so this is kind of the big point, or the sort of the big step, which is that the wave equation takes the form in these new coordinates. Well, I have minus 2c times 2c, so I get minus 4c squared. And then I have derivative with respect to eta, and then derivative with respect to c applied to u, and that's all equals 0. And so now this is an equation that's easier to solve, right? Right, and so in particular, well, I can simplify this to, since this is just a constant, now I can divide by that constant. So this is just derivative with respect to xi, and then derivative with respect to eta, and so this has to equal 0. Right. And now we can just find a solution by taking antiderivatives, right? So take antiderivatives with respect to the variable eta, and then xi to get, well, this tells me my function u has to be some function of xi plus some function of eta, and that's the general, the most general form of a solution, right? So why is this the case? Well, let me just include a little bit more details. Well, if I take antiderivative with respect to eta, this tells me that u xi has to equal some function that doesn't depend on eta, right? It's constant in eta, so it's some function of xi. And then if I take another antiderivative with respect to xi now, this tells me u has to equal, let me put a tilde, so another function of xi, and then plus something that's constant in xi, which could depend on eta, so you get some function of eta. Okay, this looks a lot like the formula that we expected to derive, and now the final step is to just plug in what are xi and eta in terms of x and t. Well, xi is equal to x plus ct, and eta is equal to x minus ct. So plugging these in, we get u of xt has to equal f of x plus ct plus g of x minus ct. And so that's the proof. Okay, and so the argument we just gave is something that's called the coordinate method, or the method of coordinate changes. Conceptually, there's not much difficult that's going on here. It's just like a lot of calculations that you have to do. The main point is, again, you just pick new coordinates. You have to do some chain rule calculations to see how these new coordinates relate to the old coordinates when you're taking derivatives. And then it turns out that because we can factor the wave equation in this special way, as we saw earlier, it becomes like a very simple PDE to solve with respect to the new variables. And in particular, you can solve it just by taking two antiderivatives and not really doing any more analysis. And then once you plug in the old coordinates, you get the solution formula we expected to be true. So this is the full derivation, which is completely rigorous. And this actually proves that all solutions have to look like this, which is what we expected from the discussion before the theorem. Okay, and so for the final part of the lecture today, we're going to now talk a little bit more about, right, so this is a nice formula if you only care about like the most general, like if you only care about like what do the solutions kind of look like in the abstract. But if you want to actually find particular solutions to the equation, for example, given certain initial conditions, the formula that we have here is insufficient for that. So it's not gonna be of much use. And so the next thing we're going to do is talk about how to actually solve this equation if you're given specific initial conditions. And so we're going to look at what's called the initial value problem for the wave equation. Right, and so you'll often see me abbreviate initial value problem by IVP, just the first initials. Right, and so what is an initial value problem? Well, let's suppose we impose certain initial conditions. Right, so in order to calculate more specific conditions, or sorry, more specific solutions. Well, as we saw with the simpler first order equations, you need some initial conditions, right? Right. And so the initial value problem is basically you're given one or two, or depending on the equation, maybe more initial conditions for the function, and assuming these initial conditions, you can solve the PDE, and so that's what an initial value problem is. And so for the wave equation, it takes the following form. So suppose I know that my function u is a solution to this equation, so utt minus c squared uxx is equal to 0, where the input variable is between minus infinity and infinity. And suppose also that I have two initial conditions. Right, so let's suppose that when time is equal to 0, right before I let time evolve, my function u is equal to some other function, say phi of x. And let's also suppose that when t is equal to 0, the derivative with respect to time of my solution is equal to some other function c. So this is the Greek letter c, which is spelled psi. And so this is like the first condition is like the initial position of the wave or string. And the second condition is the initial velocity. Right, because the second condition involves the time derivative, and time derivative is related to velocity. And so in this problem where we have some wave, which is a wave that's along the real line, for example, like you have maybe like a guitar string or something like that that has been plucked at some point. And so this has an initial position, and also there's an initial velocity that the string is moving at. And so the initial value problem is this whole problem, right? So I know my function solves the wave equation, and I have these initial conditions. And so the problem is what does the solution look like? Right, so from the previous theorem, which we proved, we know that u of xt has the following form, right? It's some f of x plus ct plus some other g of x minus ct. And so the question is, well, how do these things depend on the initial conditions? Right. And so ideally we can find some formula for our solution, for the solution u, which only involves phi and c, because then if you have this formula and you know, like you have a particular problem you want to solve where these are specific functions, you can just plug them into the formula and that'll give you your solution, right? So that's what we're after. And such a solution is called a solution to the initial value problem, which involves initial conditions on top of the differential equation. All right, and so just because we're maybe running out of time, what I'll do is, well, I'm going to write down what the formula is equal to, and then starting at the next lecture, I'll prove the formula and I'll derive it. Right, and so the theorem is the following. Right, so the theorem is basically just a formula which will solve the initial value problem, and so this is sometimes called the D'Alembert formula, named after the mathematician who discovered it. So the theorem is that the solution to the above initial value problem is given by u of xt, Well, I have a certain term that corresponds to phi, to the initial position, and this term is 1/2 phi of x plus ct minus phi of x minus ct. And then I have another term which corresponds to the initial velocity, or to this function c. And so this turns out to be 1/2c times a certain integral of c. And so the bounds for the integral are from x minus ct to x plus ct. So it's kind of a complicated looking formula, but at least it answers the question, meaning if I know what the initial position is and I know what the initial velocity is, I can just plug those into this formula and presumably solve and calculate my full solution. Right. So for example, let's suppose U solves the wave equation with the following initial conditions. So with the initial position, say U of x0 is equal to maybe sine of x, which is a reasonable initial condition for a wave because the sign looks something like this, right? And suppose the initial velocity is given by the time derivative at 0 is equal to, let's say, e to the x, right? Well, given these two initial conditions, I can use the theorem to find the solution, right? So the theorem says that u of xt is equal to 1/2, well, I have sine of x plus ct minus sine of x minus ct. And then I have the term involving the exponential. So I have integral of e to the x, or let's say e to the w dw, from x minus ct to x plus ct. And so this will, well, I can actually compute the integral on the right. So this simplifies to, well, the first term stays the same. And then I have 1/2c times e to the x plus ct minus e to the minus x, or e to the x minus ct, sorry. Right, and so that's the solution with these particular initial conditions. Right, so next time I'll begin the lecture by proving this formula. So how does this actually work? Well, we're going to use the previous theorem, right? We know that u is some function f of x plus ct plus some other function g of x minus ct. And then, well, we also know certain information, certain pieces of information about what happens when I set t equals 0 with respect to either just the function u and also with respect to its derivative. And so by combining these pieces of information together, we'll be able to arrive at the formula. Right. Okay, and maybe I just, before ending for today, I do just want to make one final comment about the physical interpretation of the formula. Let's maybe ignore the more complicated D'Alembert formula up here, which I'll prove next time, and let's just look at what we got in the first theorem today. Right. So right. So we showed that if u solves the wave equation, well, then u has to be a sum of one function of x minus ct and another function of x plus ct. Right. And so, well, what does this look like if we try to sketch it as a graph? Let's say I'll draw my function f with blue, and I'll draw my function g with green, I guess. Right, well, let's say at time, well, maybe when t is equal to 0, maybe my function is something like this, my function f. When t is equal to 0, so this is just f of x. when t is equal to 1, or let's say t is equal to 1, well, the graph, what I'm doing is I'm just really shifting the graph by some unit proportional to the change in time, right? So when t is equal to 1, I shift the origin to the point when x is equal to 1, and so this moves to the right. You get something like this, right? And so maybe when t is equal to 2, it's going to again shift, and you get something like this, right? So I have something that looks like viewing the graph of the function as kind of like a wave. It's moving to the right at speed c, right? So f moves to right. At speed c. And then if I look at the other term, well, the other term will also look something like this, but instead of moving to the right, it's going to move to the left. Right, so maybe the function g looks something like, maybe it's like a peak like this, and so this is my g of x. And so, well, now when t is equal to 1, the peak moves to when x is equal to -1, right? So this is when t is equal to 1. And then maybe when t is equal to 2, say, it again moves to the left at the same speed, right? And so what do solutions to the wave equation look like? Well, I have one function, which is like a wave, which is moving to the right at speed c. And I have another function, which is also, you can think of as like a wave, which is moving to the left at speed c. And you're looking at the superposition of these two different waves. And so the picture I have here is not the graph of u, because these waves are going to combine in complicated ways, but it at least shows like how the components of u behave, and then the full solution is given by adding these components together. So there's always one wave that's moving to the left at speed c, and one wave that's moving to the right at speed c that get added together. Maybe they interact in bizarre ways, and they're no longer moving to the left or the right, but this is like the basic structure. And so this fact doesn't change if I go back to the D'Alembert formula, right? Because here I have something that's moving to the left, and then there's another piece here that corresponds to things moving to the left, and then here's the piece that's corresponding to moving to the right. All right. Great. So that's it for today.